In this session on the respiratory system, we're going to look at how ventilation is controlled. And the image that you can see in front of you at the moment is just showing the main areas within the brainstem that control breathing rate and depth. So they show this location of the central chemoreceptors that respond to the hydrogen ions within the CSF and influence the medullary respiratory center, which composes of the DRG, the dorsal respiratory group, and the VRG, the ventral respiratory group. So it influences the breathing rate and depth through there. We've also got the dorsolateral pons respiratory centers, and those two together, they influence the DRG and therefore the VRG in terms of breathing again and ventilation. And finally, we've got the pre-Potzinger complex, and that's thought to have the pacemaker activity that sets off our breathing rate subconsciously. Now, we'll go into each of these in a little bit more detail later on, explaining exactly how they do function and what motor neurons they have, or rather, what muscles they are going to stimulate or inhibit, as the case may be, or relax. So the sessions that we're going to, or the key learning outcomes, we want to be able to look at the overall control of respiration. So first of all, we're just going to think at a very overview look at how respiration is actually controlled. So of course we have we have our respiratory centers, which are in the medulla and the pons. We talked about those two centers. But there are lots of ways or lots of stimuli coming into the respiratory centers that therefore go on to influence how the lungs respond and how ventilation responds accordingly. We have the higher brain centers, the cerebral cortex. Because the lungs compose of skeletal muscle, we obviously can have some voluntary control over these pathways. So respiration can be voluntarily inhibited, for example, but only within certain limits. Because the voluntary control that we have is overridden when the arterial CO2, carbon dioxide levels, become too high. That's basically your breaking point. And because of that breaking point, no one can take their own life by holding their breath. So we have those higher brain centers that can control your breathing, make you hyperventilate or hypoventilate or hold your breath. We've then got lots of other receptors, for example, those that might work through the hypothalamus, for example, to do with emotions and stress and pain. And they can obviously influence our breathing as well. So when someone hyperventilates due to anxiety, for example. We have receptors in our muscles and joints. Now they're thought to stimulate the respiratory centers to start breathing. When the receptors in the muscles and joints are activated, it's an indication that exercise is proceeding, so they start to stimulate your respiratory centers. We have stretch receptors present within the lungs. Now, these are present so that you can't overstretch your lungs. So as your lungs stretch more and more, they become activated during breathing in, and then that goes on to inhibit the inspiratory center neuron. An activation of this reflex pathway reduces the tidal volume, but obviously may increase that breathing rate, and it's called the Herring-Brewer reflex. And this reflex is thought to set the optimal tidal volume breathing rate combination that results in the lowest possible respiratory work. It's important to note that breathing is, of course, maintained and is adequate without this Herring-Brewer reflex, but the tidal volume tends to be higher and the breathing rate a little bit lower than is optimal. So therefore, in that case, of course, more respiratory work is required to maintain the same level of minute ventilation or minute volume of respiration. We also have irritant receptors. So if you breathe in irritants, it suddenly makes you stop breathing. It makes you hold your breath, and you can think about that if a diesel truck goes past you and all those toxins come into your lungs, particulate matter, it causes you to hold your breath or to have lower breathing rates and volumes. And then we have our chemoreceptors. So we have both central chemoreceptors, which are located in the RTN, as I mentioned earlier, and that's present within the medulla. And of course, we also have peripheral chemoreceptors, which are present within the carotid and aortic bodies. So the central chemoreceptors, which are present in the medulla, they respond to hydrogen ions in the brain CSF. And that mediates about 70% of the CO2 response, because within the CSF, the CO2 is converted to hydrogen, which binds to the central chemoreceptor. We then have our peripheral chemoreceptors, like I said, in the carotid and aortic bodies. They respond to hydrogen ions, they respond to CO2, but they also respond to oxygen levels, to low oxygen levels. And so low oxygen levels, and it has to be quite low, a 40% reduction in your partial pressure of oxygen, so that's the amount that's dissolved, they will start to stimulate those receptors and therefore increase your breathing rate and depth. So as we've already mentioned, the central chemoreceptors, they are located in the RTN, the retrotrapezoid nucleus. And so they're present within the medulla, and they're sensitive to the pH within the CSF itself. And so if we're looking at this little diagram, you can see on the left-hand side, you can see this usual CO2. So we can see the CO2 there, and you know how that reacts with water, with carbonic anhydrase to give you bicarbonate and hydrogen ions. But the CO2 can cross the blood-brain barrier, whereas hydrogen ions cannot cross that blood-brain barrier. But remember, the central chemoreceptors only respond to hydrogen ions, not to CO2. So the CO2 that crosses from the blood into the CSF is then converted by reacting with water to form your bicarbonate and your hydrogen ions, your protons, such that those protons can then bind to the receptor, lead to an increase in firing, and leading to an increase in ventilation. So basically, the more CO2 you have in your blood, the more hydrogen ions you have in your CSF, and the greater your ventilatory rate becomes. It's a relatively slow response time in comparison to the peripheral chemoreceptors, doesn't respond to the partial pressure of oxygen, but it does provide most of our response to PCO2, the partial pressure of carbon dioxide within our blood. And like I said, it does this through its conversion to hydrogen ions. And then we have our peripheral chemoreceptors. Now, these are located within the carotid bodies and the aortic bodies. It's important to note that these chemoreceptors are distinctly different from the carotid sinus and aortic arch baroreceptors that are located quite close by in the same vicinity. They're also both in areas of high blood flow, and that's quite important because these are the main blood flow areas going up to the brain and into the systemic circulation. So it allows us to know exactly how much CO2 and oxygen and hydrogen ions are present within the main circulation, the main big arteries leading to our brain and into our systemic circulation. They have a relatively rapid response time in comparison to the central chemoreceptors, but they're not as sensitive, if you like, to the CO2. They provide about 30% of the response to the CO2, which, remember, CO2 is the major driver for ventilation, but it's the central chemoreceptors that are the main driver, but they are important in terms of their response to the partial pressure of oxygen. Now, the partial pressure of oxygen is only monitored at these peripheral chemoreceptors, but it does require quite a large decrease before firing begins, and it's about a 40% reduction. And you can see why this is important. If you think the partial pressure of our blood in health is roughly at 100 millimeters of mercury, and your hemoglobin is about 98% saturated. If you drop down to 60 millimeters of mercury, PO2 dissolved, it's still 90% saturated. So you've still got a lot of leeway. You've still got a lot of oxygen overall present in your blood because it's bound to hemoglobin at this point, even though the PO2 is dramatically reduced. And it's only when the PO2 dramatically reduces below that you see this sharp decrease in hemoglobin saturation. And therefore, this is the point where it's essential that we do start responding to the partial pressure of oxygen. So in other words, it's really only need to increase respiration when the dissolved oxygen, so that's the PO2, not the total amount, reaches this level, because the hemoglobin is still 90% saturated at 60 millimeters of mercury. But like I said, there's a rapid reduction in saturation after this point. Also important to remember that the total oxygen content can actually fall to quite low dangerous levels, even with a normal PO2. For example, in anemia, so if you don't have enough hemoglobin being made, iron deficiency anemia, whatever it might be, or in carbon monoxide poisoning. So respiration is not stimulated in these circumstances because your PO2 is normal, but your total oxygen carrying capacity is dramatically reduced. Now, if we're looking at the location of these chemoreceptors are located in the carotid and aortic bodies. They monitor the concentration of CO2 and oxygen in the arterial blood, of course, but the changes in the concentration of the partial pressure of these gases trigger the firing of the afferent fibers with the cranial nerve 9, as you can see, the cranial nerve 9, the glossopharyngeal, and cranial nerve 10, the vagus nerve. And those are what transmit those signals to the respiratory centers to alter respiratory function. So a little bit of a review question. It's just an overview this, so hopefully it's nice and simple before we go into a little bit more detail. So a quick revision question for you. So just a comparison of central versus peripheral chemoreceptors. Where are they? What stimulates them? And what's the consequence? So press pause and have a little bit of a think. Okay, so we'll start on central chemoreceptors. What's the location of the central chemoreceptor? Well, of course, it's the medulla within the brainstem. What stimulates it? It's hydrogen ions, so acidosis, or indirectly by an increase in the CO2 that is crossing the blood-brain barrier. Physiological consequence of stimulation, we increase our minute ventilation. Peripheral chemoreceptors, where are they? Carotid and aortic bodies, stimulated by increased CO2, increased hydrogen ions, or decreased oxygen. Consequence, increases minute ventilation again. So nice and simple.